Okay, oh, at the end, let me forget, I have a extra credit thing I want to talk about. Let me forget. So we finished an example of a paired samples t, or dependent t-test, and we worked the whole thing, and we were on confidence intervals. Confidence intervals, effect size, and then we'll do another example. Okay. So if I'm looking at the notes, confidence interval formula hasn't changed. So the lower score is we still have that point estimate. The point estimate in this one is the mean difference. Instead of being the sample mean, we have sort of two sample means, like time 1 and time 2, or in this example, the old rec center and the new rec center. And we're really more interested in mean difference. So we've got the mean difference as our point estimate, and then we're adding and subtracting t critical times standard error. So that formula hasn't changed. Nor has the cheat for it changed. So we can use that t.test with a two-tailed test to get a two-tailed confidence interval. Or we can use our effect size code and script. I think the second one's a little faster. The slowest part is that you do have to open the F size thing and run the whole thing. Just so you get the functions you need. Make this bigger. There we go. But once you run that, ooh, access is denied. No saving for you. There we go. Once you run that, we can use this dependent t differences one. So I'm going to copy that. And that's what's on this slide. So let me talk a little bit about effect size, and then we'll get the confidence interval from the code we have. So Cohen's d for dependent t actually has several formulas, but the one in the book and the one we're going to use in this class is dependent t differences. And so we had that giant table written up yesterday, or Monday. We talked about d for single t. I don't think this was on there, but it's the mean minus mu over standard deviation. But now d for dependent t is mean diff minus mu. Remember, mu is 0. So it's really just mean difference over standard deviation of the differences. So this is sometimes called d differences because the denominator is about the standard deviation of the difference scores. Because some people have advocated a different formula that's d average that has an average standard deviation on the bottom. Don't do that one. Okay, it's in the coding for you. It says dependent t from averages next to it. You'll get numbers that don't match the book. So we're doing dependent t differences. So the denominator is standard deviation of the difference scores. And so you would run the entire effect size script, and then I included it in here just to make it clear which one we're using. So you fill in mean difference, SD difference, n. Remember n, there's only one n because there's only one sample. Alpha and k for decimals. So let's try that. So our mean difference, I have that up here in my code, but it was 857. 0.857. SD of the difference is 1.07. There are 7 people in this data set. There are 14 observations, but only 7 people. Alpha was actually 0.01 in this example, wasn't it? Am I misremembering? Yeah. Okay, so 0.01 here. And k, we'll just leave it 2 decimals, because that's good enough. So I might have done that wrong on here. Yeah, see, I did a 95 instead of a 99. But the real answer is here. So confidence interval for the mean difference is negative 0.64 to positive 2.36. So no wonder we didn't reject the null. So if you look at step 6 here, we failed to reject last time. because that includes 0. So if a mean difference confidence interval includes 0, that means that we reasonably believe there's no differences between the means. So even though the mean difference is positive, the reasonable scores, or the scores we would expect, confident in, include 0. It's not significant. This t-value should match. Just make sure we've done it right. So 2.12, 2.12 up here. My mean difference score matches my t output. And then here's Cohen's d. So really, that first line is for confidence intervals. Second line for effect size. So even though we didn't reject the null, this is a large effect. And that comes back to power. So when we did power before, this is not really in the notes. We said, what affects power? Well, alpha being bigger. So 0.05 has more power than 0.01. And that's about the cutoff score. So that's our first problem, is we're using 0.01 instead of 0.05. Talked about sample size. Okay. Larger ends have more power. We only have 7 people, so we need more people. Talked about effect size. So a larger d value has more power. I've already got a large effect size, so there's nothing I can do about that. And generally, remember, we don't really think we have control over effect size. There's not really a good way to ask questions better to get bigger differences in this example. We talked about type of test, and I said we'd come back to it. So this is the part where we get to come back to it. A repeated measures design so dependent t has more power than a between subjects design. So remember that repeated measures is every person's tested multiple times. Between subjects is each person's in a separate group. That's kind of a catch-22. It's kind of weird because between subjects usually has more people because we would need enough people in each group. But a repeated measures, you get more bang for your buck. So if we hold sample size constant, we have the same number of people in each study. Repeated measures has more power. Why? Because you've tested people multiple times. You have more data from them. And you can control for the fact that people are weird. So we use a lot of repeated measures designs in our research. Because if I ask you multiple questions, I get a better idea of what the individual differences are. That's the nice term for people are weird. And I can control for the fact that you are you the entire experiment. And the way we do that in this type of study, let me go back up and show you the data again, is that some people, when they do these scales, only use one end or the other. So when I'm rating these, like think about teacher evals, you only want to rate at the top or the bottom. And so it controls for the fact that this person's scores are at the top and that one's at the bottom, but it's the same difference score. So we can control for the fact that some people only use one end of the scale or the other. Or, yeah, let's say we're testing like response time, like how fast people react to things. Some people are just faster than others, so we can control for that. We're working on a research project right now where we're looking at final course grades. We have to control for the fact that people start at different levels, so some students are just better than others. So repeated measures designs allow us to control for unique participant stuff. And they have more measurements from each person. So while N isn't necessarily larger, the amount of data is larger. All right. So that is the end of the notes and the first example. Let's try the second example to hopefully solidify all of that together into one day. All right. brain farts.
So just a real quick question.
Yeah, sure.
On the d.div one, you have to run the f-size script first for it to
Yes.
work, right?
It needs to be
That's
over.
what I'm doing here. Cool.
Yeah, over here in functions, it has to exist.
Okay.
All right. So we did our first example. And I'm going to upload this script if you don't like yours. So let me clear everything out over here. Oh, I didn't mean to clear everything. Oh well, we'll figure it out. So I'm going to import that second data set. So import data set from text file. This is the other one on Blackboard, data 2. Give you guys a second to get that imported. So you should have before and after. I was like, oh yeah, it's fixed. And I was like, no, it's not. But now it is. All right, so we're going to do the second example. Looking at before and after. So the city is trying to determine disposal waste fees and see if that the increase in fees would have people decrease their trash because they don't want to pay as much. There have been plenty of places that have done this sort of thing where trash is more expensive to dump, so people dump less. That's sort of like a way to force people into environmental focus. So we've got the number of trash, average trash before, and then after. So we're trying to see if there's a reduction in waste. So should they increase the fee because that reduces waste? So we actually want after to be less. Okay. So let's start with our assumptions. So the first one is the DV scale. Yes, it's a ratio scale. It could be no trash bags. It would be a perfect world, but there could be no trash bags. So it's a ratio scale. Do we meet the random selection? I suppose we could randomly select because we should have access to everybody in that city. So if we focus on the city level, we would have access to everyone's trash because they're charging you a fee. If you're thinking about trash like overall, maybe not. But if we're talking about just the city, I'd probably say yes. Okay. But we couldn't randomly assign because I can't switch before and after. So I'd say we could probably select for the city, randomly assign, no way. Alright, the last one is it normal? Don't know. N is less than 30, so I can't assume that it's normal. So I imagine that the number of trash bags is probably not normal. It's probably positively skewed. Sorry, I just have to draw it in my head. Hopefully where there are lots of numbers at the bottom and very few numbers at the top. Okay. So for the research and the null, first thing we need to do is label the sample, but I'm going to label what the DV is. The DV is the number of bags. Okay. So for the sample, what we're really doing is measuring the reduction in waste. Right? So the difference between before and after. Based on what? What have we changed? Well, we're adding this fee. So we're looking at the difference in the DV, number of bags, between before and after because we added this fee. Okay, so the fee is kind of what they're manipulating, but they're using before and after as a way to see if that fee is effective. And then the population would be the difference before and after is 0. So remember we assume usually that mu is 0. So this phi has no effect, there's no difference. Or there's a 0 relationship, difference score. Sorry. So the population sample setup on these is a little different than the other ones in this section. Alright, so let's see what they want to do. So they want to reduce waste. Okay, so we want a negative number. So I'm going to say that that difference score is less than a 0. So it's going to be a less than test. And then because this is less than in the research, the null has to be greater than or equal to. So we only have 3 combos here. Now, because we're using less than, we have to make sure we subtract in the right direction. So that's this next step. So I want my mean difference score. Standard deviation of the difference score. That standard deviation is used for our effect size. The book is going to use S for that. Our standard error of the difference, that's the denominator for T. Oops, and N. And we need N for degrees of freedom. So the numbers that you write in step 3 are used in 4 and up. We're assuming that mu is 0. It's not something you have to write, but that's why over here, for the population, that's why this difference is 0. It's because we assume mu is 0. Let me save this so I can upload it. Desktop. There we go. Alright, so going back to R, I've imported my data. That's a terrible name, I think. It's chapter 10, data.2, I think. So what we've got is we've got before and after. And if I want to subtract those, and I'm expecting the scores to go down and be negative, I'm going to do before minus after. Because if before minus after is negative, wait, that would be the other way around, wouldn't it? Before minus after, that is going up. I'm saying this wrong. Yes, before minus after, this score went up from 5 to 8. That's negative 3, but that does not mean negative 3 bags. Okay, so we should do after minus before. Okay. Yeah, with me? Okay. I wasn't trying to trick you. It was really me trying to figure it out. Okay, so we should do after minus before to match our hypothesis where we want the negative score to mean that bags are going down. And you can always run this the wrong way and go back and fix it. Okay, second one. So I'm going to do after minus before. And I tell you to do is just, as you're looking at the data, see which one makes sense. So if I have 5 minus 8, it gives me negative 3, but negative 3 means it went up bags, and that's not what I wanted. 6 minus 4 would give me positive 2, but they went down. So I'm going to reverse them. Alright. So I created my difference score here, which is what we did at the beginning of the last example. So to get the mean, I'm going to take my summary of the difference score. It's got a negative 1.25. So that should be my mean difference. So it does seem like they're going down a bag and a quarter. So maybe this phi is effective, but let's see if that's significantly different. Take our standard deviation of the difference score. So it's 2.25. So that around 1.25, we're ranging about 2 bags. So some people's bag reduction is going is a positive, meaning they're actually going up in the number of bags. Some people's bag reduction is going even more negative. Right, so that's about 2 points on either side. Remember, that score can't be negative because it's all squared. Our standard error is divided by the square root of n. We've been using this little bad boy to make that happen for us. And so standard deviation divided by the length. So we don't put the wrong n in there. It's 0.80. I'll give you a second to type that if you don't have it copied. Don't let me get too far ahead of you. And then N is 8. Because I have 8 different scores, so I can see the 8 here, 1 through 8, or the 8 observations here. So we talked last time about even though we have 16 scores, it's still only 8 people. So 8 here. Alright, so part of the problem one here, I think it's at 0.05. So we're going to use p less than 0.05. We're doing a less than test, so it should be negative. The score should be negative, and that's where lower tail is going to be true. What's the other thing? Oh, degrees of freedom. It's going to be 8 minus 1, so 7. On this step, you should write degrees of freedom and the score, but I'm just telling you how I got to where I'm to this negative score. Yeah.
Can we put degrees of freedom and alpha? Can you put that in step 3?
Yeah.
And like just put them all so we have a list of that's
Yeah, that's fine. Because N is really what's driving step 4, is the degrees of freedom. But that's fine.
okay.
As long as
just
it's
weird. I like having a list of numbers.
there, as long as it's in the right, the numbers are right. Because if you miss step 4, you've obviously done something wrong on the degrees of freedom part. Or you've typed it wrong. Okay, so we're going to use QT to get our T cutoff, our T critical score. We're going to put in 0.05. I'm not going to divide by 2 because this is a less than test. So it's only one tail, so we got all of our chickens on the negative side. 7 degrees of freedom. And because this is a less than test, lower tail is true. So give me the cutoff score for 5% or 7 degrees of freedom on the negative end. I got negative 1.89. So this is our cutoff score. So I always think about this as the finish line. How far do I got to go to say this is a significant reduction in waste? So this is where we got to get to. So here's my bad checker flag. The nice thing about this is we're starting with the assumption that the mean is 0, so we actually get to start in the middle. But we'll see if that's a significant reduction by doing step 5. So this is t.test. Now remember, it's in the same order as you did the subtraction. Here you'll get a different mean, or a different sign on the mean. The number shouldn't be different. Okay, so I got my chapter 10 data 2. So I'm going to do after, comma, and then before. And I just like putting these on different lines so I can see it better. You don't have to. You can run the whole thing one giant line. We've got paired equals true because this is a paired t-test. Our alternative, ooh, can't talk. Alternative equals less. I think that's right. Conf level 0.95 because it's 1 minus p. Or 1 minus alpha, rather. So we got first mean, second mean, or first time, second time, in a sense. It's a paired test. This is pretty important, or you'll run the wrong type of t-test. We'll do the non-paired ones next week. Alternative is less, greater, or two-sided, and the confidence level matches alpha. So let's run all of that. Okay. Yes. Cool. So I got the same mean, negative 1.25. My t-value here, paste that in there, is negative 1.57. So that is not significant. So we would fail to reject. I did not make it to the finish line. Now, a lot of these are fail to reject because, one, they're examples, but sample size is really too small. So less than 30 people is just really, like, you have a hard time with them because 30 is a magic number for normality. But they keep them small so that it's not so crazy for you guys to run. The other thing that I don't think I mentioned last time is it says the alternative here in the output. So you see it says true difference in means is less than 0. So that should match your research hypothesis. So it tells you what the research hypothesis should look like. So the difference, less, so less than 0. So that population is always assumed to be 0. So that line changes based on what you write in your alternative piece. Let's try and get the confidence interval and the effect size. So our confidence interval should probably include 0. So I accidentally cleared all this out, so I'm going to rerun it. So I'm going to just copy this from up here. Let's fill in with our numbers. So our mean difference score we wrote down was negative 125. The standard deviation of the differences is 2.25. And then n is 8. Alpha is 0.05. If I run that, I should get, this time I didn't get any warnings. Yay. That the confidence interval of the mean is negative 3 to positive 0.6, which means that people are reducing their bags of trash 3 bags, but some people are increasing their bags of trash. And that includes 0, so that's why we didn't reject the null. And then our effect size is a medium effect. So it's negative 0.56. Remember, the negative doesn't mean that it's bad. It just means that the difference is negative. So the negative just tells you the direction of the mean difference. So the scores are going down from before to after. Then the effect size is a medium effect size. So the company may decide that a medium effect size is good enough for them. It may not be significant, but it may be practically very useful for their workers. So effect size adds that extra component of, while this isn't significant, a medium effect may be very useful. Okay, so I think that's it on the examples. Let me